So last week, last class rather, we wrapped up our solution of the wave equation. We found electromagnetic waves, and we found that they propagate with several basic properties. There's a speed, there's a wavelength, there's a frequency, and then the wavelength, there's an inverse quantity associated with that, which is called the wave number. And the when you look at electromagnetic waves, this is a whole field unto itself, and of course it means that there are many derived quantities that are useful. So, for instance, we could talk about plane waves, but we could also talk about waves that are having a different spatial dependence. We only talk about plane waves here, but yeah, just be mindful that that's only the tip of the iceberg. And then, so we found that there's this wave that is carried by the electric and the magnetic field, and the electric field component induces the magnetic field component and vice versa, and they keep each other going. And we found that the energies that are stored in the electric part and the energy that is stored in the magnetic part, they're actually equal. And that makes sense because these two systems are talking to one another and there's no energy lost between them. So there's no reason to assume that any of these has a preference. So then when you have that energy and it's flowing in a certain direction, there's an energy flow associated with that. And there's the that vector, the pointing vector that we talked about that describes that energy flow. So that pointing vector was E cross B with a 1/mu0, and that means that E cross B tells you the direction in which the energy is traveling. So in other words, if you flip E or B, the flow is in the other direction. So the way that E and B are set up a right-handed system of vectors that once you know what E and B are, you know unambiguously in which way the energy is traveling, and we'll use that today as well. That pointing vector was the vector that carries the energy, and it's had units of joules per square meter, and therefore if you have some kind of a surface here and you have an electromagnetic wave hitting the surface, it's going to deposit an amount of energy in that surface, and depending on what the surface does with it, it could absorb it, so it could get hot, could reflect it. There's a pressure exerted on that, and we found the equation for what that was doing. So that's plane waves, and that is the energy carried by waves. Now, before we start talking about how plane waves interact with matter, which is what we'll need to get into optics, we should talk about some of the basic properties of the electromagnetic spectrum. So so there's electromagnetic waves, as I was saying a couple of weeks ago. Optics is only one particular type of electromagnetic waves, and optics talks about what's happening with electromagnetic waves when they're in that very tiny little region of the spectrum where where our eyes can pick up the radiation and make sense of what we see. There's not really a real reason to assume that electromagnetic waves that have different frequencies or different wavelengths that are outside of our visible range, that they're fundamentally different, and they are not. The only reason why we distinguish in spectrum and wavelength is that the way that these things are either generated or the way that they interact with matter or our eyes are a function of frequency and wavelength. So we do need to talk about parts of the spectrum that are distinct, but we only make a distinction because they interact with us differently or they come from different sources. So we have the visible light spectrum, right? So the visible light, just let's call it 300 nanometers to 700 nanometers, tiny little part of the optical spectrum. If you go up in wavelength, so you end up on the red spectrum. Then you go to higher wavelengths, you get into infrared. So infrared, I'm missing my Latin or Greek roots. Infra, I think, just means beyond. So it's not visible to our eyes, but it's definitely part of the spectrum. So infrared light is still light in the sense that most optics that works for parts of the visible spectrum usually also work for parts of the infrared spectrum. So infrared light is, we use it in remote controls. So for instance, if you've ever looked at a remote control, you see on the front, there's this black piece, and that black piece is, it's opaque to our part of the spectrum, but actually the infrared can actually go through. So there's a little light that sits behind that screen. So when you press the button on a remote control, that little light, it flickers with a certain Morse code, and there's a little receiver on the other side that picks that up, and it's infrared light. So you can't see it, but just imagine that it's a little bit like just like a regular light source. You just can't see it. Now, infrared light is actually quite cool because infrared is it's also where the peak of our thermal emission sits. So when we are human body, the regular surface temperature, yada yada yada, we emit actually infrared light, and we do that more than what is around us if we're in a surrounding that is colder than us. So if we're walking around at night, and if you were able to look at our infrared emissions, you'll be able to see, even though it's not light out. So that's the principle of night vision goggles. So cool thing about night vision goggles, they're actually just regular you can make them out of regular digital cameras. So the cameras that are on your phone and on the one I'm looking at right now, they are made of these CCD chips, and they're actually sensitive to not just part of the visible spectrum, but also part of the infrared spectrum. So older CCD chips would actually still be able to pick up infrared radiation, and you could tell because when you point a remote control at it and point at it, you'd see that little light that's behind the little screen. You'd see it flicker, and you'd know that something is up. So night vision goggles use these kind of chips. Just one iteration. I'm sure there's a different version. Just one of these chips, and it filters out all the visible light and only lets through the infrared part. And now you can see in the dark. Now, that would be if your camera was sensitive to infrared light without you counting on it. That means that when you take a picture of something, you're not actually getting an accurate representation of what your eyes see. So these days, CCD cameras, they're way better at filtering out infrared light, and that's just by putting a little filter in front. So unfortunately, this camera doesn't do it anymore. But on my previous laptop, I used to be able to point the infrared. Just the remote control at the camera, you could see it blink to back it up. So unfortunately, we can't do this experiment anymore because the filters have become good. But anyway, that's infrared light. So infrared light, because it's easily transmitted by optical stuff. There was when I was an undergrad, I was working in a laboratory where we were cooling things down to really low temperatures. So for a long time, we held the temperature for the lowest space on the planet. It was 1.9 millikelvin. So that's 1.9 times 10 to the minus 3 above epsilon, absolute zero. And they would, colleagues of mine, they would take pictures of crystals that you can make out of helium. And in order to do that, you need to pressurize it and et cetera. But in order to take pictures at low temperature, you need to get an optical path going. But the problem is when you have that optical path going, that optical path will also carry just the thermal electromagnetic radiation that is coming from the room. So they have to do a really good job at filtering out all of the light, because if you're that close to absolute zero, any kind of little bit of heat that you introduce is going to kick your temperature up. So these things, they show up in the weirdest places. So that's the infrared part of the spectrum. Then if you go up in wavelength, you end up in the microwave regime. Now, so microwaves are, I usually ask this question. So why do we call microwaves microwaves? most people would say that, well, they'd have this Pavlovian response, would say that, well, it's because the wavelength is a micron, but that's not true because that's on the other side of the spectrum. Actually, microwaves, the wavelength is a couple of centimeters. So microwaves are, famously used in microwave ovens, and they're also used for transmission of cellular signals and Wi-Fi. The microwaves were first discovered by people that were running radar stations, or sorry, the heating effect of microwaves was first discovered by people that were running radio stations. So radar station. I need more coffee. Mixing up my my words. So radar. So there's a really good story about the first use of radar. So this is in the Second World War. I'm sure you've heard of this this thing that if you eat carrots, it's good for your eyesight, and that's true. But there's a story that's behind this that makes it such a perpetual thing that people keep repeating, such that they think that eating a lot of carrots is going to be a miracle cure. So here's what happened. So Second World War, Ethan, you're right. You beat me to it. So Second World War, the English had actually figured out that if you use radar, and radar is electromagnetic waves of that frequency and that wavelength that I was telling you. You can't see it, but when you have a little dish and you point it at an incoming plane, there's a reflection that you can pick up, so you can see in the dark. Now, the Germans didn't know that that the English actually had worked out how to do this, but the English didn't want to give up the fact that they had come up with this, that they had figured out how to do radar. So they spread this story that the English just had super good eyesight because they ate a lot of carrots, so they could spot these planes at night. Which is wild that that's still that was picked up, but there you go. That's why we still hear this story. So yeah, carrots. It's good for your eyes, but it's not going to make you be able to see planes at night. So people that started operating radar stations were, they would point stuff, and at some point people realized that those radar waves or microwaves, they'd be able to heat up stuff, and then that became commercially really useful because that's how we got microwave ovens. So the reason it works is there's a in water molecules, water is polar, it's got H2O, right? And they're not in planes, so they have a little dipole moment. And that dipole moment can flip around, and the frequency with which it can flip around is the frequency at a couple of gigahertz. I believe it's 2 gigahertz, 1 point something. Which means that if you point electromagnetic waves of that frequency at a water molecule, it's going to start spinning around, and now you're heating up the water. So fundamentally, that's how microwave ovens work. This is also the point where we usually need to talk about microwaves, and especially now with Wi-Fi and 5G and cancer. So microwaves are not ionizing radiation, so they cannot make mutations in your DNA. So they're not going to cause cancer. The only problem is that if you have them, if you stand in front of a radio antenna, you get really hot, right? Because you're cooking yourself. So you want to stay away from really high power sources because it makes you hot, but it's not going to cause cancer. So that's microwave. So they'll they'll use we'll use it to cook stuff. We use it for radar. We use it for Wi-Fi. We use it for cellular communications. Now the wavelength is about it's about a centimeter to a millimeter, which means that it's easily deflected by stuff. So that means that if you want to transmit a signal, you need to make sure that you have not exactly line of sight, but not too many objects in place, because otherwise it gets deflected too quickly. So the final thing about microwaves, so they're called microwaves because in a metal, the typical depth with which the electromagnetic radiation can penetrate is about a micron thick. So that's why it's called microwaves. That's also why if you look at a microwave oven, you can actually see through it. But if you look very carefully, there's usually a grid. And that grid is a metal grid. And that grid should be thicker than a micron. And because the openings in the grid are smaller than the wavelength, the microwaves cannot escape. So that's why you cook the stuff that's on the inside and you don't cook the people that are looking through the window on the outside. So microwaves. So then you go up in wavelength, you get into more broadcast territory. So we're talking about meters, megahertzes. So digital TV right now, it's transmitted at a couple of hundred megahertz, if I'm not mistaken. That's where we sit. Then you go down in frequency, you get to FM radio. So FM radio, that's in kilohertz. So for instance, if you dial into a station, KPPC 89.3, that's the only one I know by heart. That 89.3 is the frequency. So yeah, if you dial into that station, what you're doing is you're tuning an antenna and a reception circuit to that frequency, and then you can pick up that station. Now, wavelength is a couple of, let's call it a meter. So FM radio, it usually travels further because the wavelength is higher. It doesn't get as easily deflected or refracted or diffracted by stuff in its path. So it's easy to pick up and travels far. So that's why it's a good medium for doing broadcast, right? So you have one antenna and it can cover the entire basin. That's makes a lot of sense for stuff like that. But because the frequency is low, you can't really put a lot of information in it. So it's not a really good frequency range for doing point-to-point stuff like what you want for Wi-Fi or cellular stuff. But it's good enough for broadcast where you have one antenna or just a couple of stations and just many receivers that are all picking up the same signal. Now you go even lower in frequency, you get to AM radio. So AM is even larger wavelength, so it's like a kilometer wavelength. So it can actually has way longer range, and but also the quality of the audio is usually worse because the frequency is lower, so you can't modulate as much. You can't transmit as much radio, and then there's low frequencies and very low frequencies and ultra low frequencies. So for instance, there's this thing that you can do where so submarines sometimes use this. So between let's say between the Earth's surface, oceans, and the ionosphere, these you could consider two plates of a capacitor or a waveguide. And if you fit one wavelength in it, then you have a waveguide, so you can actually transmit stuff from here to there. And it has super high range because you're using the Earth, that shell around the Earth, as a waveguide. So super low frequency, so you could send Morse code through it, but don't expect to be able to tune into radio stations there. So this is what some people use. So now we've gone to the really low wavelength regime. So now we got to go the other way. So back to the visible part of the spectrum. So now we're going to go lower in wavelength. So you first end up in UV, so ultraviolet. So ultraviolet starts to become the point where the radiation becomes ionizing. So that's where you do need to be careful with exposing yourself to that kind of radiation, because it does have an opportunity to change stuff in your DNA. So it's ionizing radiation. So that's why UV light, we put on sunscreen, we wear sunglasses. And that's also why, when you stand outside in the sunlight, you get a tan. That is your body's defense to making sure that you don't get too much UV radiation. Interesting story, UV radiation, obviously, you also need that in order to be able to get vitamin D. So there are these two competing effects, but that's as far as I want to go. So that's ultraviolet. Then you go even lower in frequencies, you end up in X-rays. Now, X-rays are rays that are emitted by radioactive processes, and they're called X-rays because I believe the first time that they were discovered, they didn't really understand what they were looking at. And X being the unknown, I guess they called it X-rays. So X-rays are useful for us because we can use them to make the proverbial X-ray photos. So the reason that works is the wavelength of X-rays is about 0.1 nanometer, which happens to be the distance between atoms in a solid. So if you choose the frequency of your X-rays right, and therefore the wavelength of your X-rays right, you can scatter X-rays off of atoms that have a particular spacing and then not another spacing. So and that's how X-rays can interfere differently with certain type of tissue than other type of tissue. Then of course there's also the mass of the atoms comes into play, but that's as far as I want to go. So that's X-rays. Now X-rays obviously you want to be careful with, which is why you know, when you go to the dentist, you get a big lead shield, which should you know, make sure that your other parts of your body don't get an exposure of X-rays. And then you go even lower the frequencies, you go to gamma rays. Now gamma rays are you know, stuff that comes in through you know, also from radioactive processes, but also stuff generated in the universe far away. So that's kind of the range of the electromagnetic spectrum as we experience it. We happen to live in this very sweet spot where light is easy to pick up. It doesn't interfere too much with our biology, right? So it's not ionizing yet, and it doesn't cook stuff yet either. So we're not on this side, we're not on that side. So we're right in that sweet spot. Happens to be that actually water is also transparent in that range, which is, it's great because otherwise you know, fish couldn't see. So yeah, it's really quite nice that we're sitting right at that part of the spectrum. As I was saying before, so in optics, there's this very domain-specific language where we've developed this highly specialized shorthand way of talking about optics. And I basically need to walk you into that language from a physics point of view. I should not immerse you, start talking about optical components like lenses and mirrors yet, without explaining what's happening underneath the hood in the electromagnetic realm. So that's what we'll do today. So in order to describe optics as and the way that they interact with electromagnetic actively components like mirrors and lenses, we need to describe our electromagnetic waves a little bit more efficiently. So remember that we had our electric field when we did our first wave equation. We had this cosine, and then there was K, CT minus Z. Or using the angular frequency, we had cosine omega t minus kz. And that's the electric field. And then we had the magnetic field. There was some B naught, and it was in the y hat direction. And then we had a K, CT minus Z. And then B naught y hat cosine KT minus KZ. Now K is the wave number. Sorry, yeah. K is the wave number. But let's look at exactly what K is doing here. So when we were analyzing these waves, we said that we're tracking the way that the wave moves by studying the z dependent. So when we changed the sign here, so instead of having minus kz to plus kz, it went in the other direction. And now, for instance, if we have a wave that's not traveling in the z direction but in the x direction, we can just say replace this with x, or replace this with y if we want it in the y direction, or replace it with r if we want it in some kind of a arbitrary direction r. Now, therefore, we should be able to generalize this part of the expression a little bit to allow for waves that travel in an arbitrary direction. And then the way we do that is, so generalize, I'm blanking on my spelling, generalize for arbitrary direction. So what we'll use is K vector. And K vector is basically the direction in which it's traveling. And then what we can do is we can say, okay, now our E field has some prefactor E naught, but we don't know what that is because it needs to be perpendicular to K, and we don't know which K is. So, and then we can just write cosine omega t minus K vector R vector. And K vector and R vector. Okay. The where'd my thing go? There you go. So this is a wave traveling in the K direction. So in the case where this wave is traveling in the Z direction, you can see that. So for instance, this, just so you can see how this translates. So if you take K equals KZ hat, then if you dot that with the position vector R vector, you get K times Z, right? So you see that this is a generalization of this. I hope that that's clear. Okay, so that's for the E field, and now the B field. There's a similar K R vector, and then we say that K is perpendicular to E naught and B naught, and therefore E naught is perpendicular to B naught as well. So as long as you pick these vectors perpendicular to one another, so you don't have full freedom in picking this E naught, this B naught, this K, and this K, this is the same K. They're not independent. They need to be perpendicular to each other. And then finally, we know that the S vector, that's the pointing vector, that's going to give you the direction of propagation of the wave. So that's E crossed with B. So it's not that hard to show that K and S are pointing in the same direction. Okay, they just have slightly different units. Okay, so this is the generalization for arbitrary direction. Now, this wave writing, it's not necessarily incorrect, but it's needlessly Baroque. So we'll use the exact same thing that we were using before, where when we were dealing with a lot of things that always varied sinusoidally or cosinusoidally, and we just had to keep track of the phases and the amplitudes. And we used this concept called a phasor, and I warned you that it was going to come back. So in phasor form, E is just some E times e to the power minus I K R, and B is B naught, sloppy, minus K R vector. And that means that if you want to know E in the real form as a function of R and T, you take the real part of the E in phasor form times e to the power I omega t is the real part of E, that's the phasor form, E naught, e to the power I, and now that's omega t minus K R, K R. And that real part is, if we assume that E naught is real, cosine omega t minus K R. Okay, so this is telling you the exact same thing as this, except this is shorter because now it's just complex phase carried by this E and some prefactor. And we don't need to worry about the time dependence because we assume that this wave is was started at the beginning of the universe and will be there when all the suns have gone extinct. So let's talk about reflection. So reflection. Now we have a very compact way of describing electromagnetic waves. All we need to do is say, okay, if we have reflection off of a mirror, so reflection off mirrors. There are two ways to do this. We can draw this. So this is the mirror, and that's the reflective side. And now we can just say, okay, there's an incident wave, and the incident wave is coming in like this. So this is the k vector for the incident wave, and then the E field is like this. So that's the E field. That's the prefactor for the E field, and then B is in. That's incident. And then we're going to get a reflected wave, and the reflected wave is going to be pointing in the opposite direction, and it's going to do this. So that's K reflected, so that's sub R, and then E is pointing in the opposite direction. And then B is, let me just use capital R like a person. Okay, I'm already using a couple of assumptions here that things are going to flip, et cetera, et cetera. So I'll back that up with what's happening electromagnetically at this surface. But suspend your questions about that for a little while. Just remember what we're looking at here. So there's a wave that's traveling in this direction. So that's a wave, and the E field is doing this. So at some snapshot, you take a picture, which you can't do, but let's say you take a snapshot. That means the electric field is doing this, and now the reflected field, the electric field is doing this, and this one is traveling in this direction, and then this one's traveling in this direction, and there's a mirror here, right? This is the mirror, and then the magnetic field. So this is E. The magnetic field I'm not drawing because it's perpendicular, and we don't need it for now. Oops, E. Okay, so these are similar pictures, except this is a little bit easier, and you'll see that even with this super shorthand of describing, it's gonna get involved enough. Okay, so let's talk about what we mean by these two waves. So there's an incident wave that is E I, and I'm gonna drop the phasor form. Okay, so it has this prefactor EIO, and it's e to the power minus I k incident R vector. So that's the incident wave. And then there's a B field incident, that's BIO, e to the power minus k I R. All right, so that's the incident field. Now the reflected field, so the reflected field is some E RO e to the power. Now I'm not going to assume anything about this prefactor, but I'm going to assume that it's going to go in the opposite direction. But you'll see how that works. So that's KR R, and then the B reflected is on B r 0 e to the power I k r dot r vector. So the only thing I did is I said this is pointing in the opposite direction to this. Okay. Is what's happening at the surface. So if this is a mirror, we need to ask not only what's happening at the surface, but also what really is a mirror. So of course you've all seen mirrors, and hopefully you know what it is. But at its most basic form, a mirror is just a polished sheet of metal. So we usually don't notice this anymore because we don't make mirrors like that anymore because it's very expensive. So for instance, in the old days, people would make mirrors out of noble metals, right? So you take a noble metal like gold, silver, and you make it nice and flat, and you polish it, and then it reflects, and then you can use it as a mirror. But we don't have that kind of cash anymore, so we've come up with this other way of making mirrors. And that's actually quite clever. What we do is we take a glass pane, and then we evaporate aluminum on the backside. Now, aluminum, as you probably know, it's not reflective because usually aluminum in air forms this thing called a native oxide that makes it look dull. But non-oxidized aluminum is actually reflective. So the cool thing about this is, so you have, let's say, the glass pane, you put aluminum on this side. Now, the side that's touching the glass doesn't see any oxygen anymore. So that part's not going to get oxidized, so that part stays reflective. The back side is going to get oxidized, but that's okay. It doesn't matter because we're not looking at the mirror from the other side. So looking at the mirror from this side, you'll see glass, and then you'll see the reflective side of aluminum. So we can make mirrors way cheaper that way. But physically, the thing that's causing the reflection, it's not the glass, even though the glass itself also reflects, but I don't want to get into that. But it's the part that is metallic that causes a reflection. So we need to ask ourselves, okay, now that we know that mirrors are made of metal, so mirrors are polished metal sheets. So they're flat. That means that they all see the same phase. What is it that the metal does to these waves? And we actually already know this because we know how waves interact with metals because metals are conductors. So there are two ways to look at this. The first is that we know that E is always perpendicular to the surface of a metal. That's the first thing that we know. And the other thing we know is that if we have a time-varying magnetic field and we expose that, we expose a conductor to that, it's going to induce currents because of the EMF that gets induced. So another thing to say is B induces, actually it's the derivative, induces EMF and then a current in the metal. So these are the two things that are happening when an electromagnetic wave interacts with a mirror. So this thing, it's perpendicular. This thing, it induces an EMF. Both are fine to look at, and because we know that once we have the electric field of the wave, we know what the magnetic field is. We can use this description to figure out what's happening in the process of reflecting electromagnetic waves, but we can also use this one, and both are equally fine. Okay, but the easiest one to use is this one. So if we say that this thing is it's perpendicular to the surface of the metal, that means that if this is the normal, and it is, this is the normal of the surface, that means that when you take the electric field that is incident and the electric field that is reflected and you add them together, there can be no component of the electric field that's pointing in a direction other than the normal, right? Because the electric field needs to be pointing in this direction. So cannot be pointing in this direction, cannot be pointing in this direction. So so therefore, EI EIO plus ERO, oops. So add them together, they need to be perpendicular to the surface of the metal. All right, now it's time to put some coordinates. Let's call, this is by convention, we usually say that the wave travels in the z direction, so there's a z direction. And then let's call this the x direction. Just do it that way. I could do the other way. Actually, I had it the other way in the book, so I'm do this like this. Okay, so that's the coordinate system. There's a z and there's an x. Okay, and that's without any loss of generality, right? Because we can always pick our coordinate system however we want it. Okay, so this mirror is it's interacting with the metal, so we need to take these two, and that means that if EIO is pointing in the x direction, right? This is, hey, did I? I messed up my color codes. This is what happens when I start to do too many things at a time. So this is EIO. EIO. Okay. So if this one's in the x direction, then this one needs to be in the minus x direction, because otherwise they cannot cancel. Because the x direction is perpendicular to n, and the part that is perpendicular to n needs to be 0. So if this is x hat E R O, then if this is x hat E I O, and it needs to be equal to the 0 vector because it needs to be perpendicular to n, which means it cannot have an x component, that means that ERO is minus EIO. Okay, so this is what's happening. So we have the EIO that's pointing in this direction first, then upon reflection, it's pointing in the opposite direction. That's what I already had put into my drawing, right? But now you see that that is just because of this boundary condition where we say that the net field has to be perpendicular to the surface of the metal, and that's just because that's how metals and electric fields interact. So we know that it does this. So now we can actually say we could say some more things. So for instance, we know that the frequency is not going to change of the wave. So that's why it's that's why we can use phasor form, right? So frequency is not changing. This mirror is not changing the frequency. We'll talk about colored mirrors in a little bit, but it's not changing the frequency of the wave. So we could keep the phasor form. The other thing that it's not doing, if it's not changing the frequency, that means it's not changing the wavelength. So this Ki and this Kr, they're actually the same number. They just point in the opposite direction. So let me put that here. So omega incident is omega r. So therefore lambda incident is a lambda r. So therefore K incident is K r. And we can just call it the K vector if you want, or K, whatever you want to call it. Okay, so now it's near pod time. It's been a while. So calculate E net, which is the sum of E I R T plus E R T. This turned out to be a rather tricky problem for some of you, so I want to clarify. This. So the fact that these two prefactors cancel does not mean that the E field is 0. It means that the E field at the surface is perpendicular to the surface. So it's only the component that is along the face of the plane of this mirror. We call that the tangential component. We only need the tangential component to be 0, not the actual field. Okay, so what does that mean? Well, E net, it's going to be EI plus ER. This is in real form, right? Real form, reform, but we can start with the phasor form just to kind of figure out what's going on. And then we get, because these two are have opposite signs, we can just call it something. So we can just call it E0, okay, minus E0, because one is plus and the other is negative. So that means that the incident field and the reflected field have the same prefactor, just with a different sign. So it's going to be E net in phasor form. So now I'm writing it in phasor form. So E net in phasor form is going to be x hat times E0 times, now the thing that has the positive sign, that's let's call that EIO, doesn't really matter, we can pick anyone. That's doing the following, that's e to the power minus I k z, and then the reflected part has the opposite sign, e to the power I k z. So that's the incident, and that's the reflected, and these two together give you a sine wave. So if you remember that the sine of alpha is 1/2I e to the power I alpha minus e to the power minus I alpha, you recognize that this is a sine wave, hopefully. So this looks like the E naught times the sine of kz, sine of kz. So let me make sure I get my signs right, because I'm still missing some i's and 2 pi's and stuff. Yep, that's minus 2 times I times x hat e to the power sine kz. So the I and the 2i come from the fact that this is the definition for the sine, so we're missing a factor 2i, and the minus here comes from the fact that these two terms, the signs are reversed with respect to this one. Okay, so this is a very interesting expression. I hope that you see that. This is a standing wave. So if you look at this as a function of z only, you see that the sine wave has nodes, right, where the sine wave is 0. So at the surface, where z is equal to 0, this field is 0. Half a wavelength away from the surface, it is 0 again. And then a full wavelength from the surface, it is 0 again. And in between, it oscillates with that frequency. So let me draw that. So you put these on top of one another. You get the net field, which is doing this, and then doing this. So it's not traveling anymore. So there are nodes here, there, and there, where the field is 0. And of course, the field is also 0 here, because that's the boundary condition. And it basically fluctuates up and down. So it's like a little bit like a jump rope, right? So it goes up and down, up and down. And then if you want to convert this to real form, it's not too complicated. You just, pick up this factor I into your complex exponent. This thing is real anyway, so it comes up front. So it's not going to change the form. you just might have a bit of a phase shift because of the eye. But that's what we're getting. So we're getting a standing wave. So that's a standing wave. All right. Now, so we're getting a standing wave. Now I want to make a comment on this one, that this induces an EMF, and then the EMF induces a current. And that current, as you know, a time varying current generates, again, a time varying magnetic field. So this is a very interesting way of looking at reflection. So think about the following. So you have a incident wave comes in, right? And then at the surface of the metal, that time varying flux is inducing like little surface currents. These surface currents that are running in the metal actually cause an electromagnetic wave because, you know, currents cause magnetic fields, and that wave ends up traveling in the opposite direction. So that's perfectly valid way to look at it. And the advantage of looking at it in that direction is that it actually allows you to describe why some mirrors have a color and not. Okay, so think about the following. So you have a mirror, and now imagine that this mirror is made of you know, a metal that is not a very, very good conductor. Then if it's not a very good conductor, then it could be lossy, for instance, right? Or it could be a better conductor at certain frequencies than at other frequencies. So that means that these currents, when they're induced, they actually dissipate faster at one wavelength than from another wavelength. So therefore, this mirror could have a color because not all light gets reflected to the same degree. And this also, by the way, describes why one-way mirrors work. So you've probably seen one-way mirrors, you know, in any kind of crime thing. There's also some kind of a lineup where people are standing and you know, they see this mirror, and of course they can't see through the mirror, but people on the other side of the mirror can see. So one-way mirrors are not actually one-way mirrors. They're only one-way mirrors because one side of the mirror it's light and the other side of the mirror it's dark. So how does that work? Well, so let's make this metal. If you make it very, very thin, then when the electromagnetic wave hits the metal, it induces these surface currents. But if it's very thin, actually some of those surface currents actually make it to the other side of the metal. And then that means that on the other side of the metal, there's an emission of electromagnetic waves. And that means that if you make a thin metal film, that mirror actually is transparent. Okay, so, but it's not super, super transparent. It's only transparent for a little bit. So let's say this is the interrogation room or the part where people have the lineup, and this is where all the police officers are sitting. Then if you make this room light and this room dark, then this bright light goes in, gets reflected, and a little bit of that light comes through here. And then because people here are in the dark, they can actually see what's happening. But because people here are in light, they cannot see the light that's coming from here because these people are in the dark. So there's not a lot of light coming from here to there. So by the time that light comes here, it's not detectable anymore. So therefore, you know, if you're doing this, and sometimes this happens in police dramas, somebody, some dingling comes into this interrogation room, turns on the light, all of a sudden people can see who the people in the other room are. So it's only one way because one room is dark and the other is bright. Let's talk about a situation where the wave, when it's incoming, it's not coming in at a right angle, but it's actually coming in at an angle with respect to the mirror surface. So it starts off very similar, right? We start off with a wall here. So this is time where I break up my ruler finally. All right, so this is our mirror surface, and then there's an incident wave. And the incident wave is coming in at an angle. So what do I mean by that? Well, it's coming in, let's say like this. So that's K, incident. And if this is incident, then the moment it hits the surface, there is an angle with respect to the normal that we need to quantify. So let's do this. It goes in this direction. And this is the angle, theta. Now this is the incident angle, so theta sub I. And now we can ask ourselves, what happens with this incident wave when it gets reflected? Okay, so we'll use the same boundary condition, and the boundary condition is that E tangential, net tangential, is 0. So that is again because mirrors are made of metal, and in the most ideal case, metals don't have, you know, these surface currents stay super on the surface. We don't talk about half one-way mirrors or anything like that. We just say that is what it's doing. Okay, now let's put a coordinate system on. So we've got, let's call that the x direction, and let's call this the z direction. And the electric field is pointing in a direction that is perpendicular to this. So the incident field, we'll just write it in phasor form, because that's the only way to remain somewhat sane. So we'll just keep it general. We'll say EI, e to the power minus I, k I dotted with the position vector. Okay. Now, in this case, if this is ki, then and this is our coordinate system x and z, then that means for the k vector is it's just a simple straight trig problem. It's k times the sine of the incident angle plus the times the x hat plus the cosine theta I times the y hat. Okay, that's the k vector. Now this thing is going to get reflected, and then I'm going to draw it already at an angle that is equal but opposite to this one. But because I'm taking a step ahead, but you'll see mathematically that works out. So the this is the reflected angle. So the reflected field is some r o e to the power minus I k r, and I'm leaving it as general as possible for now. And that k vector is it has that same vector k because again this thing is not changing frequencies, so frequency doesn't change, wavelength doesn't change, and therefore the wave number doesn't change. In this case, the wave is traveling in the opposite direction because theta r is on the opposite side, which means that the z component changes, but the x component does not change. So we still have a sine of theta r x hat minus the cosine theta r z hat. And now I see that I made a mistake here. That's Pavlovian. Z hat. Okay, so so it's traveling in the opposite direction. There you go. Okay. Now, the boundary condition that this is 0, that is at the surface. So if we want to evaluate this at the surface, that means that we need to pick a position for the surface, and we might as well pick that position at the surface where z is equal to 0. So I'm going to place that surface there. So the incident field at z is 0 is, so if you multiply this out, right? So this part is going to, when you take the dot product, you get a ki dot r. Then the z component is going to multiply with that part that has the z unit vector. That part we're going to set to 0. So this thing is going to disappear, and this thing is going to be the one that remains. So we'll get a k, a sine theta I, and the x hat is going to be dotted with the x hat in the position vector. So we'll get a am I missing? Oh shoot, I'm mixing up my colors again. Sorry. EI, I like red colors. EI at z is equal to 0 is going to be just our EIO, e to the power minus I kx sine of theta I. So the ER at z is equal to 0 is ERO, e to the power minus I kx sine theta r. Okay, so that's the E field. Now there are many ways in which you can look at this. There are some more baroque than others. I want to try to use the most simple version of looking at this. So let's see at what's happening here. So there's an x dependence, and then there's a sign, which means that for certain parts here, the field at a certain time is 0, and then a certain part here the field is 0, certain part here the field is 0. In between that are distances that are the wavelength of the wave projected on the surface. So let me show you what I mean by that. So there are these parts that are perpendicular to the wave vector that are giving you nodes and antinodes. Now these points are moving. So this is a snapshot in time. So we're not assuming time varying fields right now. So this is what we're going to call lambda, but it's lambda incident tangential. Okay, it's the tangential component on the incident field. And this part is the part that is reflected. Let me make sure that I'm going to end up right. So that's the reflected part. And then there's similarly here a lambda reflected tangential. Okay, so that's the distance here, that's the distance there, and it is related to those sine waves, those sine equations, right? There's x and then there's sine. So this distance, for instance, when theta is 0, this distance becomes infinitely large, right? But if theta is these become short. These get shorter and shorter and shorter, and at some point the tangential wavelength is equal to the actual wavelength on the screen. Okay, so what does it mean that the tangential field is 0? Well, that means that when we add these two together, that the tangential field needs to be 0. So we'll add these. So So E net is going to be this plus that. So it's EIO e to the power minus I k x sine theta I plus ERO minus I k x sine theta R. All right. Now, the tangential component is going to be carried, encoded in this part. So EIO is the E field of the incident wave, right? So let's say this is K, then let's call this EIO. All right. And then the field that is reflected here is going to be pointing in the opposite direction. That's ERO. Okay. So the sum of these at the surface need to have no tangential component. What does that mean? Well, we're going to find an EIO that's going to have an X and a Z component. So there's going to be some X times something geometric, cosine and a sine with pluses and minuses, and there's a Z component here. There's going to be something similar here. There's going to be an X component and a Z component. And now we're talking about the fact that the parts that add up for the X need to add up to 0. So the part that is the part that needs to be 0 is the tangential component. So that means that we'll get a prefactor here times X times this exponential, and then we'll get a prefactor here times X times this exponential. And that whole thing needs to be 0. And it needs to be 0 for all X. And because it needs to be 0 for all X, these two exponents need to be 0, because we'll get a equation for the prefactors, and those prefactors are just numbers, right? The prefactors are just numbers. They're just something that says how big that wave is. But the prefactors have some relation. But then if they were, if now we pick a different point in X, so point here, point here, point here, point there, those prefactors still need to guarantee that the net field is tangentially 0 at the surface. So that means that these two exponents need to be 0, because otherwise we cannot meet that boundary condition. So we'll get, this needs to be 0, so E tangential needs to be 0 at the surface, which means that there is a relation that I don't want to talk about because it's messy. There's a relation between EIO and ERO, and that's a sloppy and. There we go. And this is important, that e to the power minus I kx sine theta I must be equal to e to the power minus I kx sine theta r for all r, for all x. So any point on the surface, these two need to be the same. So if this has to be the same for all x, and the k's are the same, that means that the sine theta I and the sine theta r are the same. So therefore, and that is the thing I was going for, theta I is theta r. And that, ladies and gentlemen, is the condition for reflection. So as I was saying, wave comes in like this, gets reflected, goes off to the other side. On the other side of the normal, and these two angles, incident and reflected angle, they're actually the same angle. They just happen to be on the opposite side of the normal. So I try to go through this exercise at a somewhat higher level because, like I was saying, it's very easy to get stuck in trig hell. And really what you need to realize is that the structure of this equation. So you can write out the components, but in the end, you will still get something of a prefactor that has an x and a z component, and it's also multiplied by this exponent. And here, something with an x and a z component multiplied by this exponent. And if you factor out the x components, you'll have an exponent for one part and an exponent for the other part. And they need to be the same for all x's. And because it is for all x's, that means that these angles need to be the same. So hope that you follow that along. So that is really the fundamental principle with which we can dive into geometric optics. So next class, we will start talking about mirrors that are not necessarily flat, but they are curved, so we can get image formation. And then the thing that's doing the work is this condition. Just remember that this condition comes fundamentally from the basic mechanism with which electric fields and metals talk to one another. So let me just repeat. So the tangential component is the part that is perpendicular to the normal or along the plane. So tangential is, this is tangential, is in this direction.